Poznan University of Technology.
To continue a bit of history, so as I said, essentially all, commotion around neural networks started in the 1950s. First neural network models have been built back then, with a famous perceptron, for instance. Then, for certain reasons which I don't have time to go into, the progress in the field stagnated for mostly in the 1970s. Then we faced so-called second spring of neural networks somewhere starting in the late 1980s up to 1990s, maybe even at the end of millennium, where there was quite intense research, and we did also some research in those days using neural networks as well. But then actually at the beginning of this millennium, there was a very strong progress in other branches of machine learning. So if you ever heard about models like support vector machines, for instance, or probabilistic models like, again, graphical models or Bayesian networks, those models, or logistic regression, statistical methods, all those methods actually witnessed very strong progress around, in the first decade of this millennium. And it was only somewhere towards the end of that first decade of this millennium where actually more or less deep learning started. And that deep learning, which we observe today, which is indeed a continuous progress, of machine learning in this particular branch, is essentially a quite fortunate happenstance of co-occurrence of conceptual developments in the field on one hand, and also availability of large data, which is quite often required by deep learning models to train efficiently, and thirdly, availability of huge computing power, right? Because important thing is that somewhere also beginning at the beginning of this millennium, people started realizing that a typical PC, personal computer, a laptop or whatever, nowadays, when it comes to compute, doesn't have only the CPU, but also has the graphical processing unit. And those graphical processing units, because of the demand of the gaming market and so on, they became more and more powerful. And somewhere like 20 years ago, there was that realization that we can use those, we can harness that GPU power for actually performing computations which are unrelated to gaming, right? And for instance, one of the first famous projects that involved that was that famous Folding at Home project, which was launched by, I think, Stanford University, where you could download a software from Stanford University, and that software would use your GPU, your graphical processing unit, in background while you were working on your laptop or PC for protein folding experiments, right? So. And that was like a starter of it, and then deep learning folk also noticed that there's such an opportunity. Yeah, and of course again, I'm of course butchering here the history of AI and machine learning in 3 slides, so it's really very, very superficial. But of course, it's very important to remember that all that is the work of many humans and many respected people. I'm listing here some names that subjectively to me matter a lot in this area, and I think objectively as well. No time to cover them in detail. I know perhaps I'm just emphasizing here the fact that some of the achievements of some people in this branch of AI were so much appreciated that in 2018, if memory serves, 3 of the respected researchers in the field, Joshua, I think it's read actually Joshua, not Joshua, but Joshua Bengio, Geoffrey Hinton, and Yann LeCun, obtained or were granted the so-called Turing Award. Turing Award is a reward granted by the ACM. The ACM is the Association of Computing Machinery. It's the most respected, professional organization in the field of computer science. It's a bit similar to IEEE, that many of you may know, but it's specific for computer science, and that's why it's actually this Turing Award is being recognized as sort of, a Nobel Prize in computer science. Indeed, great achievements or contributions of those guys. Geoffrey Hinton, absolutely, a star in the field. He worked on neural networks already in the 1970s and did a lot of interesting contributions. Yann LeCun, by the way, is one of the major like popularizers of the convolutional neural networks. He started working on them in the 1990s, and that's exactly the type of architectures that we will be particularly paying most attention in the rest of our meeting today. Okay, yes, so I should probably skip this slide because, that sort of already percolated from what I was telling you so far, namely that nowadays deep learning is widely recognized as one of the, actually not one, actually the dominating and the state of the art and the most promising, as a matter of fact, probably too, branch of machine learning, right? Because it's actually percolated, or actually, transfused to many branches or application areas of machine learning, and it's actually setting state of the art in many benchmarks, practical applications, and so on. And we are benefiting from that on a regular basis. Speech recognition that we use on our phones, smartphones, is based on deep learning most of the times. Speech synthesis as well. You might be using Google Lens, which can tell you what this object is, right? When I'm going for walks, I often ask my Google Lens what variety of plant this thing is, right? And it will tell me in minutes, right? Just by taking a picture of it, yeah? And so on and so forth, yeah? So lots of those actually everyday tools that we are using nowadays actually have some backend in computing, in deep learning. So now let's move on to really the concrete stuff, right? And by the way, I've been informed that there might be the case that there will be some overlap with what you've been told perhaps yesterday by Professor Brzezinski. If at any moment you feel that this is really redundant and you feel competent already in this slide, please let me know. We can move on faster if you'd like, because I have enough material to fill this entire day. So this might be like a repetition of what you already heard, but maybe still worth doing. So a typical unit in neural networks is essentially a dot product of a vector of weights and scalar signals that are being fed into a unit, extended with a so-called bias. That bias is so-called free parameter of the unit in the sense that it's also learnable, meaning it's also tunable in training. And essentially, it's called bias or offset because it's just being added to this weighted sum. Then actually, it shifts the objectively, so to say, absolutely the output value of the unit, which is y. For mathematical elegance, we quite often do this following trick that rather than having this b term as a separate term in the formula, we assume that there's an extra input to the unit with the index 0. So you can see that here we index from 0 to n, not from 1 to n. And there's an extra input associated with that, extra signal associated with that input with index 0. And there's a constant signal like +1 or -1 actually fed into the unit through this particular input. So functionally speaking, this formula is equivalent to this one, but it's more elegant because, now the bias becomes W0, right? So this is one of the so-called weights or parameters of those units. And overall, when you hear parameters in the context of deep learning, you mean the parameters, those weights essentially of units. Typically, we are not talking about individual units, but about layers and more larger entities within a deep network. And when I told you 2 hours ago that the ChatGPT has those billions of parameters, then these are those parameters I meant, right? These are those weights, yeah? Distributed across different units, different layers, different modules of a given network. Okay, so that's actually covered in this slide. Then, quite importantly, a single unit of this type is called a linear unit because it performs a linear projection, so to say, of this vector on some output value. Yeah, it's a linear combination, so it's in terms of, as we understand it in linear algebra, right? As it turns out, these types of units are not particularly powerful computationally speaking, in the sense that, in brief, I think I have a separate slide on that. If you have a linear unit or many linear units, and then you will try to combine their outputs, the y's of those units, with another linear unit, then what you get is a linear combination of linear units. And as you may recall, which is sort of obvious, I hope, if you have a linear combination of linear combinations, then functionally speaking, this is still a single linear combination. So combining or connecting linear units to each other doesn't bring you any new capacity, so to say, computationally speaking. That's why a typical unit or typical neurons or units in neural networks at deep learning are equipped with nonlinear activation functions, which, simply speaking, take this raw dot product or weighted sum value and pass it through some nonlinear mapping. Nonlinear mapping, like I will move forward a bit, like these ones. So these are exemplary activation functions where this weighted sum is here on this horizontal axis, and this blue line shows you how this raw excitation value, or the output of the linear unit, is being mapped through this particular unit. And we have a bunch of different types of nonlinear activation functions with different pros and cons that we may touch upon later, right? Okay. Yes. As you may have noticed, right, a single unit is really primitive in the sense that you may notice that this is actually, it's a memoryless thing, right? It doesn't have like a state as we put it in computer science and engineering, right? So you cannot, mathematically speaking, it's just a function that maps from inputs to outputs, and that's it, right? Nothing is being written down, so to say, or memorized by such a unit. There are exceptions from that. There are certain more sophisticated types of units and layers that can perform, like for instance, memorizing of input signals, or some aggregation or some integration over time, for instance. But most units in ordinary neural networks and deep learning systems are memoryless or stateless. Good. Now, it's probably also useful to learn the concept of a hyperparameter, namely, in deep learning context, by parameters we mean just weights. Essentially, anything else that decides about the shape of your model, for instance, how many units you are using, how they are being connected, how many inputs your units have, and so on and so forth. These all are hyperparameters. Yeah? The critical difference is that you are responsible for picking the hyperparameters of your model. Yeah? The designer has to decide about the architecture of the network, layers, units, and so on, while parameters themselves are being automatically tuned by a training algorithm, typically based on the gradient descent concept. Okay, maybe I'll skip the rest. I think, yeah, I said that at the bottom of the slide. Good, I think we may move on. Okay, just for completeness, I'm also mentioning that there are not so common, I would say quite rare nowadays, different types of units which define this, which replace in brief this weighted sum, this dot product, xi, wi, with something else. That something else could be, for instance, a Euclidean distance between the vector of inputs and the vector of weights, which seems to be useful in certain applications. But frankly speaking, this is very, I would say, unpopular nowadays. It's an interesting branch of research, but I'm just mentioning that for completeness. Yeah, so this has been already said. I think that we typically feed this linear quantity through the activation function. I'm using the sigma symbol here for this activation symbol because because one of the most common types of activation functions are so-called squeezing functions. And the word squeezing starts with S, and hence the sigma letter, right? By squeezing function, we mean functions that take this x argument, which is again the weighted sum, yeah, and map it to a closed interval, like the interval from 0 to 1 in case of the sigmoid function, right? Or the interval from -1 to 1 in the case of the hyperbolic tangent function. So whenever you face an activation function of this kind, of this type, we call them squeezing functions. But there are other functions of that type. I think I'm trying to sort them out here, mathematically, so to say. So in general, we have activation functions which have bounded codomain, and these are those S-shaped essentially, like hyperbolic tangent and sigmoid function. But there are also such that have unbounded codomain, and definitely the most popular of them, or most famous of them, is rectified linear unit, which is this kind of function. Where, again, it's a very primitive function in a sense, just a combination of two lines, and can be expressed with this formula, right? Essentially, yeah, because you just ask what is the x. If x is smaller than 0, then you return 0. If it's greater than 0, you return simply x, right? That's it. But formally speaking, indeed, this is a form of nonlinearity. And by the way, this and these activation functions here are much, so to say, modern, so to say, than these ones. When people were playing with neural networks in the previous millennium, so to say, and previous century, and like 1990s, for instance, they've been mostly using actually these types of activation functions, which has certain downsides. Without going much into detail, as you've heard from me and possibly from other lecturers in previous days, deep learning models are trained with gradient descent, which calls that, actually points to the fact that the basic concept behind training contemporary deep learning model is the gradient. Gradient is a vector, which is a composition essentially of derivatives, right? Derivatives taken with respect to different parameters of the model. And derivative is a simple concept that I'm assuming we all know. And derivatives, we may recall from high school that derivatives of a constant function is essentially 0, right? And all those S-shaped functions, they have actually the the property of actually asymptotically approaching some limit in minus infinity and plus infinity. So it would be the limit of 0 here and 1, and here the limit of -1 and 1. So that they flatten out at the extremes, yeah? And they are getting flatter and flatter, which means that the gradient there is essentially 0. It's very close to 0. And because of that, units equipped with this kind of activation functions will be quite prone to so-called problem of vanishing gradients, where actually, if it happens that my unit has excitation which is far from 0, somewhere here or somewhere here, and in training I will take a gradient or the partial derivative of the output of that unit with respect to the parameters, that gradient will be very close to 0, and this will typically harm the efficiency of my training. So, and because of that, one of the important contributions of contemporary deep learning, somewhere I would say, actually the idea is quite old, but actually it got popularized, like 15 years ago, is to use these kinds of activation functions, which are in a sense more primitive and may give rise to different problems, because, for instance, this can go to infinity. So you may actually, for instance, witness some problems with instability of your training. But on the other hand, the advantage is that you may see that, okay, for the negative argument, the gradient the partial derivative of ReLU is 0, but for the positive argument, how much is it actually? So a question to check whether you are asleep or not yet. So what is the derivative of ReLU for the positive argument here? It's 1. Yeah, exactly. It's 1, right? Because it's just it's x, right? For the positive argument, ReLU is nothing else than just an identity function. It's just x, right? So the gradient of that or derivative is 1. And importantly, that derivative is 1 in the entire positive part of the domain, right? So even if the excitation is 1 million, right, then still the gradient will be 1. So it's constant, and it never actually vanishes, right? And this actually proves to be really useful in training neural networks. But of course has the disadvantage that for the negative argument, there's no gradient at all. And indeed, such units or units equipped with ReLU activation function may as they put it, in the jargon, they may die, right? Meaning that at some point they may actually reach such a configuration of weights that they will never actually experience any non-zero gradient. That's why the more sophisticated variant of that is so-called leaky ReLU, which as you can see is essentially a combination of two straight lines with slopes. But then importantly, this part of this function has a non-zero slope, right? So which means that it's still nonlinear, which is important for the reasons I mentioned before. But you will also get a non-zero gradient even for the negative arguments. And it's also constant. That gradient will be 0.1. Okay, let's skip this one. Again, some of you may be, okay, so maybe just a question. How many of you have at least a gist of the idea of the gradient descent algorithm or gradient optimization? Okay, so there are some people in the audience. So conceptually speaking, all gradient optimization algorithms are based on this, derivative concept, right? And they are essentially trying to find the setting of the parameters based on that gradient. And still, I would say the downside of this kind of functions is that you experience, or the algorithm will experience, very sudden change of gradient, right? Because if the algorithm happens to be, or the state of the unit happens to be somewhere here on the positive side, even if it's like 1/100th or something, right? The gradient will be +1. Now let's assume that we, as a result of changing the parameters, we move slightly to the left-hand side and we enter the negative part of the domain. So let's say the excitation of the unit is now -100. So the change of the behavior of my unit is very tiny, right? But the gradient will change very abruptly from +1 to from 1 to 0.1, which is a huge change. And this may cause all sorts of instability of the behavior of the training algorithm. That's why this is yet another motivation for actually making it even more sophisticated and considering functions like this one, so-called exponential linear unit, which combines this positive straight line with this kind of curve given by this equation, which is actually just an exponential function, thanks to which we have a similar behavior than here, but we have a smooth transition from negative to positive argument. There's actually, mathematically speaking, this function is non-differentiable at 0, right? Because the series of the derivatives actually from the right and the left hand side, they do not meet at the same value, right? But actually they here converge at the same value. Okay, so anyway, the essence is here, I hope. Yeah. Now, importantly, so as a matter of fact, this was like ABC, so to say, of neural networks. And frankly speaking, nowadays, we rarely talk about deep learning in terms of individual units. A unit is a tiny part of my model and typically not worth particular attention. Especially nowadays when we build huge models with millions of units, we tend to talk about models more in terms of layers. When a layer is essentially some composite of units. Yeah? In the simplest form, it might be just like a sequence of units arranged in some way, right, and used together as a software component which I can plug in at some point in my model and combine with other models. So for instance, typically in PyTorch or TensorFlow, you will have a class, a data class which represents a single layer, and you will just, call a constructor of that class, if you are familiar with this kind of terms from programming languages, and you will ask, please create this kind of layer for me, and this layer should have this number of units and consequently perhaps this number of inputs. Right? Yeah, so this is what is happening nowadays. Yeah, no, actually that's the essence of it. Yeah? Yeah, actually I have 2 slides on that, which I forgot. Yes, so that's the essence here. Let's parse the slide while, I try perhaps to, okay, yeah. The potentially more novel part may come here, namely, Indeed, the simplest layer will be just like a sequences of units. I think I have some. Okay, it's too far. Okay, I won't go there. I have some examples further, but actually you can try to arrange units in more sophisticated structures, so to say. And one of obvious structures is a matrix. And this is particularly true when you deal with images, right? Because our images, two-dimensional images, can be perceived as matrices. So you can take an input image, right, and arrange units in a two-dimensional grid, right? And this is what we quite often do, and essentially convolutional layers that I will delve into a moment later are exactly such entities. Yeah? They are essentially arrangements of units which are distributed across x, y dimensions in a certain manner. And so these are two-dimensional arrangements of units. And you can take it, of course, further, right? You can go into any number of dimensions. And in my memory, PyTorch and TensorFlow nowadays have prefabricated components for up to 4 dimensions, I think. Because, for instance, a 4-dimensional data structure might be useful for instance, processing 3-dimensional movies. But we have 3 spatial dimensions plus time dimension, right? But if you'd like, you can implement a 10-dimensional layer. And because in mathematics, whenever we leave 2 dimensions and go further, we should not talk about matrices anymore. We should talk about tensors, right? And so essentially, so that's why actually, typically when you work with neural network libraries nowadays, you typically use only the term tensor, right? Whether you talk about vectors or matrices or more dimensional structures. Okay. Yes. Okay. Yeah. Important point to mention is that one of the reasons why we don't talk about units anymore is that moving on to the level of layers is more consistent with what many trained engineers used to do with linear algebra, right? If you have a vector of signals and you would like to produce another vector of signals from them, then one of the obvious things you can do is, in linear algebra is to multiply this input vector of signals by a matrix, right? So this is just a matrix multiplication of a matrix and a vector, and this is, so in other words, it's a linear projection, so to say, of this x to some space of y's, and this is essentially nothing else that what a single layer of linear units is doing, right? So that's essentially exactly the same thing. The difference is that all those units are arranged or the weights of those units are arranged into that 2-dimensional matrix. Okay. Yes. So yeah, I think yeah. In this slide, I'm mostly signaling that, of course, what I'm covering here are just the basics. There are much more sophisticated layers used in deep learning nowadays. One example of them are, for instance, so-called recurrent layers, which are useful for processing sequences, like, for instance, sequences of tokens in natural language, or sequences of signals in time series, or sequences of events, and so on. So, for instance, there's a famous, actually probably the most famous type of recurrent networks called long short-term memory, which looks like this internally. And as you may see from the diagram, it's already a bit more sophisticated because actually it engages multiple linear layers and some activation functions. And interestingly, it actually has a state, right? It has a memory. So actually it has a internal variable which has a certain initial value, and consecutive calls or invocations of or applications of this kind of layer to data update its internal state. No time to go into that. Very interesting architecture, but the gist again being that the whole idea in deep learning to some extent is to take those elementary concepts and build higher and higher levels of abstraction by building more sophisticated concept and units and composites of them, right? So we have units at the very bottom layer. Then we have layers, like simple layers, like linear layer, convolutional layer, and then on top of them, we can build even more sophisticated structures like this LSTM layer, and so on. Yeah, and now, even though we haven't actually entered yet, the domain of convolutional neural networks that we should talk about in a moment, it's probably worth to just at least briefly talk about what can we do actually with this kind of units, what they can compute, because I guess for at least part of you, it might be a bit challenging, you might be struggling. How is actually this about computation, right? We are talking about some, essentially simple multiplication of numbers. Is it really, it's not a proper computing like, programming in some programming language and so on. Yeah, as a matter of fact, it is, and I will try to demonstrate that to you. Here, just some preliminary slide that simply emphasizes that indeed the computation that is happening in neural networks is fundamentally different from what we mean by computation. Because, I guess what many of you may mean by computation. Because first of all, it's continuous, right? Meaning we actually always work with floating point numbers, right? So something comma something, right? Something 0.73, right? 0.73 and so on. There are specialized models in deep learning which perform integer valued computing, but it's not so common, right? Essentially, we should look at deep learning as a domain of continuous computing. Then this is a distributed model of computing, namely, it will be very often the case that in a given layer, or even more than a single layer, the processing will happen simultaneously. And because of that, we can parallelize this kind of computation very conveniently on, for instance, those graphical processing units, GPUs, because they by default have the hardware architecture which is very good for actually parallel computation. Or even nowadays, quite often we are using a specialized hardware which is actually dedicated, actually has been built by NVIDIA and other players in the market to meet the expectations of deep learning models, because the demand for deep learning is so huge that it is worth nowadays actually to build specialized hardware, like so-called TPUs, right, tensor processing units, that's actually exactly what we want for this kind of models. Yeah? And importantly, maybe that's particularly important, it's worth emphasizing that deep learning performs non-symbolic computing, right? So a lot, if you happen to be familiar a bit, with other branches of AI, which I mentioned in the previous lecture briefly, like decision trees, for instance, decision rules, so-called frames, what else? Case-based reasoning, for instance. All those things where models or approaches were quite symbolic, meaning they assume that there are certain symbols representing, for instance, parts of my program and so on. Deep learning is very different from that, right? Actually, it doesn't really exhibit any symbolic structure. And that's actually one of the disadvantages, right? This is one of the reasons people often complain about deep learning models as being black boxes, right? Because they are huge conglomerates of continuous computation, in hundreds of thousands of dimensions, which cannot be easily understood, right? So this is one of this lack of so-called explainability is one of the huge challenges for deep learning. Okay, that's probably the hardest slide of my entire lecture, and because of that, we'll just give you the gist of it, just to signal that it's not that we are, blindly, and walking through this, story of deep learning without any theoretical underpinnings. As a matter of fact, there's a lot of theoretical works in deep learning and machine learning, which actually gives it pretty good, formal footing, with certain, theoretical proofs that actually evidenced what can be really computed, right, with a neural network. And one of the most famous of them is so-called Sybenko theorem, which is actually, again, everyone is quoting or citing this particular work, but as a matter of fact, there was another guy that came up with the same idea in the 60s. In brief, the implication of this theorem, which I'm showing you without the proof, is that neural networks are so-called universal approximators. meaning that they are actually they can approximate, or in other words, okay, they can fit any data arbitrarily well. Yeah, by fit I mean learn from it actually, or mimic the behavior of the function you want to train. So actually, in principle, you can do everything with them, meaning that there's, simplifying that a bit, there's no input-output function that cannot be implemented with neural networks. I'm simplifying that a bit, but because as a matter of fact, if you look at the assumptions of this theorem, these assumptions are narrowing down the class of functions that can be approximated with neural networks to a certain class, but this is still a very broad class, right? Which in practice means that there's no mathematical function that cannot be approximated with a deep learning model arbitrarily well. Arbitrarily well meant in terms of the precision, right, of the error of approximation, epsilon, which is seen in this particular formula, which is a strong result, right, because it tells us that they're really powerful in terms of expressibility, and actually this theorem tells you that this arbitrary precision or approximation degree can be obtained with just 2 layers of units, and that's it. You don't need anything more, right? Actually, if you have enough units in those layers, you can do and approximate anything you want arbitrarily well. And of course, on one hand, that sounds amazing, right, and very, very, very tempting, and we benefit from that. But on the other hand, this theorem doesn't tell you anything about the generalization capabilities of a neural network, right? Because this theorem tells you that if you know certain function, of f lowercase f, then you can approximate it with a neural network uppercase f arbitrarily well, right? But in practice you don't know that function f. In most cases, it's not that you have some mathematical function that you would like to model with your neural network. You have a set of examples, right, of input-output pairs, like those images I was showing to you with those fundus imaging. And those examples form a sample of your functions, right? They don't tell you everything about the behavior that should be learned, right? It's just a number of examples, and you are never certain whether those examples are representative enough for what you would like to learn. So that's very important to remember, that this is a nice theorem, but actually it doesn't tell you much about the implications for learning. And actually, I'm saying that, so that actually I'm actually translating this previous slide here to a sort of human, parsable, so to say, natural language. Also with that footnote, right? Exactly. So it says that the theorem actually tells you only about the existence of that function. And actually, the theorem even doesn't tell you how to arrive at that function, how to create that function, how to set those parameters, right, of those weights. And most importantly, it's completely unrelated to generalization. But probably it's good to keep in memory this bottom of the slide, to have, again, a gist of what actually those models can do. When you look, let me go back to, to the behavior of the formula of individual units. So individual unit is a linear projection, right, of a space of inputs to a continuous value, right? And then we typically feed that output, that y, through a nonlinear function like this one. What does it mean in terms of, let's say, operating on some data? Assume that we have a data set, a simple two-dimensional data set. So we have only x1 and x2, right? So we have 2 inputs to my network. And we have examples that represent 2 classes of objects, class A and class B, right? Then that's already a fairly reasonable, machine learning problem. Yeah, your task is actually to use those examples to create a machine learning model which will predict for you, based on the values of x1 and x2, whether a given point on this plane should belong to class A or class B, right? And when you have, imagine first that you have a single unit of this type I just mentioned. So that unit will be actually, technically speaking, just it would be just, that weighted sum, but look, I can actually unroll this weighted sum, and now I can say that this will be x1 times w1 plus w2 x2, of course, right? Yeah, because that's a special case of that formula, plus that b, but that's not so important. And perhaps I will be passing that through ReLU, right? ReLU applied to this. That's it. Yeah? So when you look at this, this is nothing else than a function, linear function of two parameters. So you should imagine this as you should imagine a third dimension here, sticking out here, right? Which actually is this value. Right? And then this value is actually thresholded by the ReLU function. And for some values, for some arguments, which means for some points on this plane, the output of ReLU will be 0, because we know how it behaves, right? And for some values, for some combinations x and y, of x and y, the output of ReLU will be positive, right? So in other words, the very simple neural network of this kind, comprising just a single unit, will operate or actually act as so-called a dichotomizer, right? Dichotomizer meaning a binary classifier, which takes those points on the two-dimensional plane and maps them to some decision class, or attempts to map them, right? But because it's of this form, the only that it can do actually is actually map this linear combination to 0 and non-zero, which in practice would look like this, like this shaded region, right? In other words, this kind of classification that can be implemented with a single unit of this type is a linear classification. It's a linear classifier, essentially, very similar to so-called logistic regression, for those of you that perhaps heard about it. So it's not particularly sophisticated, right? And you can tell that actually this kind of model cannot actually nicely delineate class A from class B, right? Because there's no way in which you could take those parameters W1, W2, and B, which you can tune them, right? And tuning them will actually, what it will do, it will move this plane to the left, to the right, to the top, to the bottom, rotate it, and so on. But whatever you do, there's no way for those particular division plane to nicely cut off A from B. There's no way. Yeah? So what we do, what is the practice of deep learning, and neural networks, of course, as well, as a simpler case, we combine them. Yeah, we take, we take a layer of, such units with ReLU, and on top of them, we create another layer. We build another layer, and we feed the outputs from the first layer to the inputs of the second layer, which means now that the units in the first layer will still do this linear thing here, right? We'll try to divide that space into two half planes, so to say. But the second layer now will take those individual signals and combine them. Yeah? And it will be able, the second layer will be able of combining them in a way that actually can cut out from this plane convex shapes, right? So it's already better, right? Arguably, what this model can do is arguably better approximating what we would like to achieve when faced with this classification problem. And I think you can also guess that with each consecutive layer, this capability will only grow. So actually, technically speaking, once you have this third layer, you can also create or carve out, so to say, non-linear or non-convex shapes. So in principle, with a few units of this type, you could actually design a neural network that would perfectly carve out class B, so it would be perfectly delineated from class A. So that's the essence, and especially when you look, when you attempt to solve with deep learning problems, classification problems of this type, right? Class A versus class B. Okay, and by the way, there's a very nice example that shows that we essentially in practice really need that, right? We need to combine, to stack layers upon layers, because if we don't do that, then there are even apparently super simple problems that cannot be solved with a single layer. And a very common example here is the exclusive OR problem. So the super simple classification problem where you have just two input variables, and the output variable is defined as so-called symmetric difference between the inputs. So this is what the input should be given, output should be given inputs. So in 3 dimension, you can imagine that these 4 data points as these 4 circles, right? And if you now think about it, there's no way for you to find a parameterization of a single unit with those weights W1, W2, and B, such that would, tell apart those 2 examples from these 2 examples. Okay. Yes. And now, okay, so actually, and I think we are more or less finishing now what I wanted to say in this particular section. Now, a few examples of ways in which actually we typically combine units into deep learning architectures and neural network architectures. So as I said, the most common thing is to combine units into layers. So such a single sequence of units would be considered a layer, a linear layer, for instance, one-dimensional layer. So this network is essentially a composition of 4 layers, 4 units in the first layer, 5 in the second, and then 2 layers with 3 units each. And typically, when we stack so-called layer, these kind of layers, which by the way are also called dense layers, we call them dense because when we stack them up, on top of each other, then you can see that each unit in the next layer consumes, so to say, or gathers signals from all the units from the previous layer. So in other words, you have as many connections between 2 consecutive layers as there can be, and hence you call this kind of architecture a dense network, right, or dense layer. Yeah, there are exceptions to that, but this is a common thing. Also, typically, we do not have shortcuts, but there are exceptions to that as well. Yeah, and by the way, the kind of network I showed to you some time ago, that one for the segmentation of those fundus images, actually had this kind of subnetwork here. So actually, what was the further part of that model was a dense subnetwork at the very end of it. But in a moment, we will talk specifically about actually this, so to say, early part of these models, namely those convolutional layers, because they are specifically designed to handle images. But this will come in a moment. So, in other words, this is a combined or hybrid, I could say essentially, neural network architecture, which comprises a dense subnetwork at the end, but this subnetwork is preceded by a stack of convolutional layers at the front, meant to, being fed with images. Okay. And this is essentially almost the same, with the exception that this. Okay, maybe I'm a bit simplifying. Namely, what you saw in the previous slide corresponds to this part of this slide, where we have, again, here dense layers, right? But those layers are actually fetch signals from a stack of convolutional layers, which are here. Where the difference is that all this is happening here in 3 dimensions. So, because this architecture was designed to handle not 2-dimensional images, but 3-dimensional images, which are also quite useful. Again, as I said, there are other architectures or other types of layers. I mentioned this recurrent neural networks. So this is essentially just another diagram showing that LSTM architecture. I may also mention, that there are many experimental, so to say, architectures that are played with, for instance, for theoretical reasons. One of the eldest one of them is the Hopfield network, which actually was created or proposed by a physicist, which is so-called fully connected network, where we have essentially only one layer of units, and all those units get signals from themselves, meaning that actually every unit is connected to every other unit, and they form so-called clique. We call it in graph theory, we call it clique, which is a graph in which every 2 entities are connected to each other. But this is actually, I cannot say that this is an architecture that has any practical implications at the moment. I'm just mentioning that for completeness. Yeah, and now finally, I would like, because that's very important, I would like to move on and talk about specifically deep learning architectures and entities that we need to use deep learning in the context of images, applied to images. And the concept we need here for that is the convolution and the convolutional layers. To sum up a bit what I said before, you may recall me saying that it is the designer like you, right, who actually designs the architecture of the network and decides about all the hyperparameters, how many layers, how many units, and so on, which activation functions, and so on. Once you have it and you have your training data, you can train your model on that training data, in other words, fit that model to your training data, and that process will result in the parameters of your model, namely those WIs, being tuned in all the units in your pipeline. In practice, what you really need to that actually are three things. So as I said, the training set, a given network architecture that we'll talk about in a moment, and actually I showed you some examples already, but there will be also something called the loss function, which defines actually what is the correct response for the network, namely essentially learning or training of deep learning models is an optimization process. Optimization meant as a minimization of a certain function, where the algorithm is trying to tune those WI parameters and minimize the loss, where the loss is a function that measures the similarity of the output of your model to the desired output, to the thing that your model should produce, right, for this particular input. Okay, and I think, you know what, I would probably change the order because I don't think I would like to go to the specifics about about convolutions. Yeah, so I think that architecturally speaking, this is the most important thing. Yeah, I think so. I will go back to those slides perhaps later. So what is actually the elementary building block of deep learning architectures used in computer vision? It is the convolution operator. Convolution operation is a very simple elementary operation, actually invented by mathematicians like 300 years ago for all sorts of reasons, actually, and it's a part of the calculus, part of mathematics. And but it proved to be very useful in signal theory and signal processing, time series processing, already like 100 years ago. And now we are using it essentially in images because, as a matter of fact, image can be perceived as a two-dimensional signal. So the formula I'm showing to you here is the formula for convolution for a single argument function, right? So there's a certain function f, because you can see, and that function has only one argument, like time, right? And that function is being convolved with so-called mask or kernel, and that's the convolution operation. And all that is happening in a single dimension. So this is actually how you define convolution for time, for signals in time domain, right? Like time series, right? Like when you do some prediction or forecasting, this is how you would write it down. But please notice that essentially, there's no reason why actually this function could not be two-dimensional or have two actual arguments, x and y. And if that function has two arguments, I think it's coming, quite late. Is it here? No. It comes with one of the further slides. Sorry, I'm just through here. Then if you have something like f on xy, then this is nothing else than a two-dimensional image, right? Which expresses the brightness of a pixel at location x and y. That's why we actually adopt the convolution operation to two-dimensional images. And that operation actually is super simple. It's nothing else than actually multiplying the values of pixels by some values, scalar values, given in this matrix or mask, as we put it, or kernel. And so when you look at it, this is nothing else than a dot product again, right? So actually, it's very similar to that wi times xi, which should bring you the realization that essentially convolution is nothing else than dot product, with the difference being that this dot product is shifted over time axis or shifted over image, as I will demonstrate in a moment. And other than that, so because of that very nice convergence, we are essentially, it becomes so obvious to take those neural network units that I talked about earlier and let them process pieces of image. And this is actually what is happening in convolution. Let me perhaps move on and explain it visually, because that's probably, those slides that were covering that in a moment ago, they might be helpful, but perhaps for individual consumption, so to say. So what is actually happening here in convolution is that you should imagine that there's my input image, perhaps a monochrome input image, so it's a X dimension of that image, Y dimension of that image, and this is like a single channel. Yeah, so it's monochrome image. We have only one value per pixel. So, and these are these pixels, and these arrows represents a processing conducted by a single convolutional layer. What that layer is doing is actually looking at this input image through the viewport of a mask of values and multiplying those values, multiplying the brightness values of those pixels by that mask. So actually calculating that dot product, right? And as a result of that, as in a regular neural network unit, what you get at the output is simply a single scalar value, and that scalar value becomes the element of this output image. Yeah? In more general terms, this is the input tensor, and this is the output tensor. Right? And now imagine this happening actually, or shifting this entire system across X and Y axis, and repeating this operation for every pixel, every window, input window in my image. First of all, please notice that this can be done in parallel, right? Because actually the results of that calculation for individual pixels are independent, and that's why we are so happy to use GPUs for that. Right? And on the right-hand side, you can see actually the same thing being done, but not for monochrome image, but for an RGB image. So we have now a 3-channel input image, right? And now this convolution operation is essentially looking at a small fragment on the input image, like just perhaps 3 by 3 pixels, right? And also at the same time at all 3 input channels simultaneously, and combining all those values in this kind of formula, just a weighted sum, by multiplying all of those values. There would be actually 3 by 3 by 3, right? So 27 values. Each of them will be multiplied by a separate parameter W, right? And the weighted sum of that extended by that B parameter will become this output of this particular unit. Right? And again, this will be repeated across the entire image. And in essence, that's a convolution. Right? This is actually what is happening here. And sorry for skipping this formula for the sake of brevity, but essentially, when you look at that, this is exactly what is happening here, right? And for simplicity of those formulas, if you'd like to inspect them later on, I'm keeping them one-dimensional because when you uplift them to 2 dimensions, they become a bit hairy, more indices and so on. But overall, this is exactly what is happening here. Now you may also notice that essentially, why not repeat this process multiple times for the same input image? Namely, and indeed, this is how we typically implement nowadays convolutional layers in contemporary deep learning. Namely, we allow them to do the thing I just told you, but multiple times. Meaning that we essentially do what we did here, but multiple times with different kernels or weight matrices, right? With different sets of WIs. Which means that, for instance, if I provide my layer with 2 such sets or 2 kernels, then that layer will be able to apply the kernel of those weights to my input image once, and the second kernel separately, which means that the output of this operation will be a 2-channel image, right? Because for each input window, this layer will be multiplying this fragment, this 3 by 3, let's say, fragment of my input image by one kernel and by the other kernel, right, in terms of dot product. And you will get 2 independent scalar values, which will form again, those the values of two channels of that input image or output image, or in other words, output tensor. And again, you should still imagine this happening all over the place, right? All over the input image, right? And indeed, you know, when you look at the diagrams in deep learning papers or tutorials and so on, you will quite often see them presented this way, where people just talk about how many channels my input tensor has and how many channels my output tensor has, right? And that's it, because these are the key parameters or hyperparameters of my layer. Plus, of course, an important hyperparameter is the size of that kernel. Typically, that size of the kernel is 3 by 3, but we can use greater. We can also use others, but maybe I'll skip that for now. Yeah, so that's essentially, if you get this, you are quite at home, so to say, in the sense that you have some gist, of the idea what those convolutional layers are actually doing. And that's indeed the case. That has certain implications in terms of how many parameters such a layer will have. So there's a specific formula. Importantly, there might be quite many parameters. So for instance, it turns out, let's assume that we have, if you have a convolutional layer which has a kernel size 3 by 3 xy, and has actually 16 input channels and 32 output channels, then the total number of parameters for such a layer will be almost 5,000, which may sound like a large number, but as a matter of fact, it's not that large by today's standards. And quite importantly, that's probably quite important realization you should have at this point, is that this number of parameters does not depend on the size of your input image, right? Because conceptually speaking, all the processing at a given moment happens here, right? At the particular position of my window in the input image, right? I'm producing some output, and this is all happening in parallel over all pixels of my image. And that image could have, 20 by 20 pixels, but it could have like 20,000 by 20,000 pixels. And the operation, of course, in that second case would be much more expensive computationally, but the number of parameters doesn't change at all, right? And that's a very convenient feature of convolutional layers, that they are, at least certain classes of convolutional models are, how to say, neutral when it comes to the size of input images. You can process images of any size with them. The only cost you pay for that is actually is the computational cost. Oh, by the way, just a small remark, a small footnote, because again, not enough time. As a matter of fact, we quite often even employ so-called one-by-one convolutions, in which that kernel size is just 1 by 1 pixel, which is actually a bit surprising, right? Because that means that those output channels will not be able to combine values of neighboring pixels. And normally in convolution, this is what is so important for us. The convolution operation was designed actually, in a sense, let's put it that way, to combine, the values of neighboring pixels so that we can detect edges, or for instance, corners of objects, or so-called T-junctions and other features, right? And this is indeed what is happening in convolutional networks, but occasionally we can even do this kind of thing, so-called one-by-one convolution, which also makes sense, because even though it has no spatial extent, right? Because we are working with every pixel individually, yeah? Then still those output channels from that operation will be combining those input channels in some non-trivial way, which might be useful. Okay, yeah. So and maybe importantly, now imagine this whole thing happening layer by layer, right? And this diagram in the lower right corner is actually trying to depict that. So we have some first in layer. This may be like input image, monochrome image, or maybe this is the output of some earlier layer. But let's assume that this is the input monochrome image. The first layer, marked with this arrow, takes this input and convolves this with the mask, and produces this tensor. The second layer produces this tensor. Crucially, the essence of this diagram is to show you that with each consecutive layer, there's a spatial compression of information, meaning that looking from the backwards, so to say, in this model. So this pixel, this element of the output tensor, depends on this window, this part of my input of the previous tensor, right? Because let's say this convolutional operation uses 3 by 3 kernels. But this tensor, in this tensor, each pixel like this one depends again on 3 by 3 neighborhood in the previous tensor, and so on. So as a matter of fact, if you combine these dependencies together, this particular element of the output tensor depends on all these pixels in the input image. Yeah? And this is, by the way, what we mean by so-called receptive field. Yeah? So with each consecutive layer added, convolutional layer added to my model, I'm increasing the receptive field of those units. In other words, to put it trivially, with this particular sensor, my network can see this part of the input image. Yeah? And that's exactly what we quite often want, right? Because the whole idea of image interpretation is that we perhaps start with very elementary features of my input image, like, as I said, like edges, corners, T-junctions, and so on. And on top of them, we build, higher level concepts, right? Such that the human eye, the image of a human eye requires some corners, right? Perhaps some edges, and so on. So by combining, those primitive elementary features into something more complex with those consecutive, receptive fields, each layer can implement more and more sophisticated concept, visual concept. And this is exactly what is happening in convolutional neural networks. And there were many works that actually empirically were showing that those units in consecutive layers were implementing more and more sophisticated concept. And I think I have some examples here. Yeah, so that's quite important, I think. So this is the concept of receptive field. So this is like a summary. Okay, yeah, that's let me skip that. That's not so important. These two slides, I think, are more or less about the fact that the implication of all that is, it's quite well visible here, is that, as a matter of fact, principally speaking, you cannot compute the result of convolution at the very edge of your image, right? Because if you do that, the kernel would stick out of the input image, and you cannot actually move out of your input image. You don't know what are the pixels there because there are no pixels anymore. So you have to deal with that in certain ways, and there are some practical ways of handling that, and one of them is that you simply accept the fact, and you allow your tensors becoming smaller and smaller with each layer. And this is quite common. The other one is actually to complement your input image or your tensors with a border, with a margin, additional margin of artificial pixels, and that practice is called padding. I think it's mentioned here, right? So padding is the practice of actually adding, fake pixels around your image, like a frame to your image, so that the kernel can still fit, so to say. And that padding is typically, default padding is so-called zero padding, when you feel those pixels are assumed to have the value of 0, with some ups and downs. Then, again, very briefly, by default, we are assuming that that kernel of the convolution, that window, is shifting over my input image pixel by pixel. So in other words, it's like row by row of my pixels and column by column, right? But in general, it doesn't have to be so, right? So by default, in other words, we are assuming that the stride of the kernel is 1, right? It shifts, by 1 pixels in every conceptual step. But it can be actually greater. And quite often we, for instance, mandate, or we require my convolutional layer to actually, for instance, move with a stride of 2. So move every second pixel, actually. So we are shifting that window by 2 pixels, and horizontally, but also vertically. What is the result of that? The result of that, if we use the stride of equal to 2, is that the resulting tensor will be twice smaller. right? Which actually would be half the size of the input tensor. And as a matter of fact, we quite often we would like to have it, right? We would like actually to, because so often, as I was sort of explaining already, we want actually the model to compress the information about the image into something more compact, especially when we solve like classification tasks and similar tasks. The image might be like hundreds by hundreds of pixels, but at the output, so it's like even an image 100 by 100 pixels, that's already 10,000 pixels, right? It's quite a lot, and that's a small image, right? And from that, we would like to obtain something very like global, right? Like an indication to a like decision class, for instance, blood vessel, non-blood vessel, right? So we need that compression, right, of information, and using stride greater than 1 actually allows us to achieve that. Okay, yeah, and there are some other, hyperparameters of convolutional layers. So one of them is that activation function that we've been talking about. So as a matter of fact, similarly to dense layers that have activation functions, also convolutional layers have activation functions because the same principle still holds. If you were not using activation functions in convolutional layers, then by composing one convolutional layer with another convolutional layer, you would be composing a dot product, right, weighted sum, right, with another dot product or weighted sum, in other words, which is a weighted sum of weighted sums. In other words, you would multiply this thing times yet another W3, and that would be again, right, just a linear combination, nothing. You wouldn't gain any additional conceptual added value, and because of that, we need non-linearities, right? So in a typical convolutional layer, we'll have a non-linear activation function as well. I'll skip this. Yeah. Okay. Yeah. It's probably worth mentioning that it's not the case that convolutional neural networks can contain only convolutional layers. Occasionally, we introduce some other types of computations between those layers, and one of the most popular ones is so-called pooling, which in brief means any type of operation which conducts the pooling of information, meaning spatial aggregation of information. And the simplest possible pooling is just maximum pooling or max pooling, which is a very simple operation. It's essentially nothing else than applying the maximum operator to patches of my input image to windows. So in similar spirit, as I was explaining to you, that we are shifting that convolutional window over the input image and multiplying the elements of the kernel, the weights, by pixel values. Here we are calculating simply the maximum of pixel values. So for instance, for a 4x4 input image, one channel image, a monochrome image, and a window of size 2x2 moved with stride of 2, the outcome of the maximum operator or max pooling operation for this particular image would look like that, because simply speaking, the maximum of these 4 pixels is 4, right here. The maximum of this 4 pixels is 8, right? The maximum of these 4 pixels is 5, and so on, right? You can play with this, meaning you can use different stride, different kernel size. Importantly, this is, in a sense, even simpler operation than the convolution, because it's non-parametric, meaning this feature or this layer or this operation doesn't require any parameters, any weights like this one, right? So, in other words, it's non-trainable in the sense that you cannot tune any parameters here. But it has the advantage of actually, again, compressing or aggregating the spatial extent of your image into something smaller, and that's why this is one of the reasons we use it. Okay, we'll skip this. So this has certain there's some interesting nuances, namely deep learning models are trained by, as I said, gradient descent, which requires actually taking or calculating the gradient of the loss function with respect to every parameter of the model, every W of the model. And that, mathematically speaking, that requires that the entire model, the entire possibly very deep neural network, with multiple, maybe dozens of layers, has to be differentiable, mathematically speaking, differentiable end to end. Yeah? And technically speaking, the maximum operation is not differentiable. And this, so this has to be resolved in a certain way. Fortunately for max pooling, it's quite easy, and this slide explains that, but I will, again, for the sake of brevity, I will stop it. I will also actually skip this particular thing here. That's actually, this slide should go, together with the other one that talked about the platforms. Actually, I said that sort of. So I will skip the slide because I don't want us to get distracted. I'll probably skip this. If time permits, I may come back to that later. And at least, because, as you may know, only this part actually of our meeting is recorded, is taped. So at least, I will start actually now covering those, milestone architectures that build on top of this idea of convolutional neural networks. So this part of the lecture is meant to actually show you really the truly full-scale deep neural networks that have been built using this concept of convolution and other concepts, and we really had a huge impact on the field. There are thousands of deep learning papers nowadays, if not probably hundreds of thousands, but I'm just picking those that were really like highlights, and really had a huge impact on the field. And one of them is definitely the AlexNet architecture, which was essentially the first super successful or really successful deep neural network for image classification, which has been proposed in actually, 2012, and presented at a very famous conference at the time. But most importantly, it also was shown to outperform other approaches, used in computer vision back then. So actually, more or less, this is the moment where people, have been exposed to the idea that with contemporary deep learning networks, you can really build image classification systems that are as good or even better than what has been considered a state of the art of computer vision about a decade ago. Let me perhaps first go to the explanation of this particular architecture, which is actually built on using the components I explained to you. So I hope everything should be more or less clear. You can see that this is again, the kind of diagramming that we've been using. So all the tensors have essentially, spatially speaking, they are two-dimensional, x and y, but this third dimension here is the number of channels, right? So what this network accepts as input is a 3-channel image, 3 because RGB, right, red, green, blue, of dimensions 224 by 224 pixels, because that was the size of images in the so-called ImageNet database, which is freely available and you can play with it, which became a famous benchmark for developing image classification systems. So this is the input to the system, and now you can see that the first convolutional layer in this model uses kernels 11 by 11 pixels, 3-channel, right? So actually you can already tell that this, for a single channel here, the number of parameters will be 11 squared times 3, so it's 121 times 3, so it's 363 plus 1, actually plus bias, right? But this thing is repeated 48 times, so because this first convolutional layer actually creates or computes 48 different values per each pixel from this input image. So from actually, you can see that actually from a 3-channel image, we are actually expanding that image into 48 channels. And this is a very common practice in deep learning architectures used in computer vision, because we want to allow this model to come up with all sorts of features that are needed to solve the final classification task, which is, we face somewhere at the end of the model. So quite often we actually already at the very early stage of the model, we have quite many features. Because, features. Why I say features? Because in a sense, every channel of this tensor can be considered a separate feature. Technically, indeed, yes, it's a separate feature, local feature, calculated from this input image using a window of 11 squared pixels. And then you can see that this sort of blueprint repeats, several times. So we have 1, 2, 3, 4 another convolutional layers with different hyperparameters. So the next one actually looks at this tensor using 5 by 5 kernels. But of course, those kernels have also 48 channels, right? Because this is the number of channels in this image. Yeah. So each element of this tensor depends on this block, this chunk, so to say, of data taken from this thing. But of course, again, please don't forget that this is all happening in parallel over all parts of my image, right? So this is like, you can imagine this window shifting across this entire tensor, and so on and so forth. And I hope that you can see that, with consecutive layers, that allows this entire architecture to compress the information and gather information coming from different parts of the image into more and more sophisticated features, which is accompanied with the lowering spatial resolution of the image. Because you can also tell that because this first layer uses stride of 4 pixels, then this tensor is 4 times smaller on X and Y than the input image. That's why this tensor has already only 55 by 55 pixels. Yeah? And this is again repeating. So for instance, here we have also max pooling, which I will skip. Because of that, we have 27 squared, 13 squared, so that actually finally the last convolutional layer produces a tensor which is only 13 by 13 pixels small. So it's much, much smaller than the input image. Yeah? But that's what we want. Yeah? We want actually this entire information about the image actually compressed into something much smaller, spatially speaking. But on the other hand, the number of channels is quite sizable. It's 128, even though actually it was even greater here, right? And now, this is a critical moment in a sense, because here in a sense, this information which is conveyed by this tensor is still a spatial information. It's about features, right? About different features occurring in different parts of my input image. But now, what is the goal here? The goal is classification. We want this model to recognize different types of objects and images. So to arrive at that final classification, we need to map this information to the vector of probabilities that my input image represents a given decision class. In that particular benchmark, that ImageNet benchmark, there were 1,000 decision classes, so quite a huge number. That's why what follows in that AlexNet model is a stack of dense layers. So those simple layers I was explaining closer to the beginning of our meeting, and actually just 2 layers, one after another, and but actually quite large. Each of those layers has 2048 units, and the first of those layers actually gathers signals from this entire tensor, right, and maps that to 2048 dimensions, because this is the number of units in that layer, and the number of units in the layer determines the number of output signals from that layer. This is happening twice, right, with 2 different layers, which means, of course, also 2 different parameter sets. Each of those layers has a separate set of weights. And finally, you have a totally final layer, which actually maps that to 1,000 units. Actually, that last layer has 1,000 units. It produces 1,000 values. And that last layer uses that sigmoid activation function you may recall, which means that it will produce actually a value in interval from 0 to 1 per each output, for each of those 1,000 outputs. And that value will be interpreted as the probability that this model points to a given decision class. And that's it essentially, right, in brief. So the key here is that we have a continuous processing model that starts with image features and actually is able to create more and more sophisticated features, which are then mapped to something that is more global, right? Because actually starting from this part, we are not talking about images anymore, because these arrows here are already vectors. Actually, these blocks are vectors. These are not images anymore. They are flat in a sense, yeah, because they come from linear, from dense layers, not from convolutional layers. And thanks to that, we can map it to those indications to decision classes. And in brief, because I should be probably closing in a moment, this model, designed in this way. There are many technicalities I'm skipping. For instance, those guys actually ran that model or distributed that model on 2 GPUs. And that's why this diagram looks so weird, right? Because actually, so this pipeline here at the top works on or runs on one GPU and the other one on the bottom on the other GPU. Yeah? So that's why it looks like this, but that is actually essentially a technicality. But most importantly, those authors of this paper were able to show that the rate of error that this particular model committed was actually significantly smaller, or actually definitely on par with the state of the art. While the whole model, as a matter of fact, was much simpler to design and train than those manually crafted features that I was talking about at the very beginning of my first lecture. And this is a sample of the results that this model can produce. So in each of those insets, you have an input image, and below the input image, you have the correct label. So actually, this is the label that the model should point to, actually, and indicate as the most probably in that 1,000-dimensional output vector. And what follows is the distribution of the 5 labels or 5 decision classes that the model found most probable for this image, right? Sorted by the probability. So these bars here actually correspond or depict probability. So you can see that for this image, the decision of the model was correct. It was considering different types of classes, including ticks, starfish, cockroach, and so on. But actually, for mite, it produced the greater probability. So the greatest probability. So it's actually indication or decision for this particular model was image was mite. Similarly, for this image, and this image, you can, by the way, see that the confidence of the model varied, right? So because this absolute width of this bar matters. For instance, it was very certain about this container ship here, while it wasn't so certain about the mite here, perhaps because the mite wasn't completely visible, right? So it's actually at the edge of the image. But of course, it doesn't mean that this is perfect. And at the bottom of the slide, you can see the cases in which the model made mistakes. For instance, for this image, the correct class is grill, but the model actually pointed to convertible as the most probable class. But actually, you can see that the grill was the second most actually likely according to model. And by the way, this also actually shows you that some of those labelings are, I would say, controversial, right? Because if you, as a human, were asked to classify this image, some of you would say that this is a convertible, some of you would say that this is a grill because it's such a prominent feature of this particular image, and so on. So of course, it wasn't perfect, but it was good enough to actually stir a lot of commotion around deep learning at this, those 12 years ago, and started that revolution, meaning that start the realization in the community that you can really achieve a lot with deep learning. And because of that, this is essentially one of the really fundamental and milestone works that started that revolution, and that's why it's worth mentioning. Plus, on top of that, essentially most of convolutional neural networks we are using nowadays are more or less actually repeating this kind of blueprint with certain extensions. And for those extensions, we will use this last part of our meeting that will start at 2 p.m. With that, thanks a lot, and let's have some time for lunch. Thank you.
Poznan University of Technology.